What I'm about to explain to you is probably the stupidest thing that statisticians have ever done. Hello. So, you know how in statistics we fit models and stuff? Like, let's say we fit this model to data. Y is equal to B0 plus B1x plus E. And when we fit statistical models, we kind of, sort of, not really, but not, we do. We don't kind of, sort of, we do. When we fit these models, we make assumptions about these E's. Residuals. We make 4 key assumptions. If all this is foreign to you, I'm going to link a video somewhere to diagnostics and why we make these assumptions about residuals. Anyway, we make 4 key assumptions. Therefore, yes, 4 of them. Normality, homoscedasticity, which means that you have constant variance across all your x values, linearity, and independence. I'm not going to talk about independence today. What I'm really talking about is associated with these other 3. Normality, homoscedasticity, and linearity. So, yeah, long story short, we fit these models. We make these assumptions. So how do we know if we violated these assumptions? Good question. Well, let me tell you what we used to do. And unfortunately, some people still do this. The old, dated, dumb approach is to use hypothesis testing.
Yay!
Yeah, seriously, you know how I feel about hypothesis testing. But that's how we used to do things. The null hypothesis would be that the residuals perfectly follow a normal distribution, and the alternative would be that they do not follow a normal distribution. And then we ask, all right, if the null is true, how likely is it that we've observed the residuals that we've observed? For this video, I'm going to focus on the tests of normality, but the same would apply for any sort of tests, like tests of heteroscedasticity or tests of linearity or whatever. The null hypothesis would be that the residuals follow a perfectly normal distribution. Let me say that again. The residuals follow a perfectly normal distribution. Emphasis intentional. The alternative would be that they do not follow a normal distribution. And what our hypothesis test is going to ask is, all right, if the null hypothesis is true, how likely is it that we'd observe the residuals that we actually observed? And then you would compute a p-value associated with that. And so there's different flavors of normality tests. There's like the Anderson-Darling test, the Kramer-von Mises test, the Kolmogorov-Smirnov test, which is the funnest test to say in statistics. Probably. Kolmogorov-Smirnov. But you have to say it with a Russian accent, because I think they're both Russian. Let me double check though. Smirnov was Russian, and Kolmogorov was Russian too. So I was right. Yeah, but you must say it with a Russian accent. Kolmogorov-Smirnov test. It was Kolmogorov-Smirnov test. My apologies if I'm butchering a Russian accent. Anyway. Yeah, so lots of different ways to test it. But there are 3 potential problems with using hypothesis tests to evaluate assumptions. And these are kind of a big deal. Which is why I'm going to argue you should never, ever, 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 ever use a hypothesis test to evaluate assumptions. Problem number 1. And maybe this isn't that big of a problem, it's just kind of weird. So the first problem is that we have a different relationship with the null hypothesis than we normally have. Normally, when you are doing a hypothesis test, you want to reject the null hypothesis, because the null hypothesis means there's no difference between the 2 groups, for example. And you want there to be big differences between the 2 groups. And so you are incentivized to have very large samples so that you could reject the null hypothesis. Because if your sample is huge, then you're more likely to support your alternative hypothesis. But with assumptions tests, we do not want to reject the null hypothesis. Because if we reject the null hypothesis, that means that our data do not follow a normal distribution. Or that our data are not homoscedastic, or that our residuals are not linearly related, etc. Basically, yeah. It puts us in a different relationship with the null hypothesis where we're kind of incentivized to have small samples. Because with small samples, you're more likely to retain the null hypothesis, which is what you want. So that's kind of weird. But an even bigger problem, which I've already alluded to, is that these tests are super duper, super duper, super sensitive to sample sizes. But again, in the opposite way.
Oh, now wait a minute. But regular hypothesis tests are sensitive to sample size too.
Right you are, young Padawan, but it's different here. Because, like I said earlier, you're incentivized to increase the sample size. And a large sample size is never a problem. And so increasing your sample size, yes, makes it more likely to reject the null hypothesis, even for trivial differences, But we want large sample sizes. We've known this for a long time, that the larger your sample size, the better you are able to detect any sort of difference between hypotheses. So what does that mean? That means if your sample size is too small, you might have massive departures from normality that will never, ever, ever be detected because your sample size is too small. Likewise, if your sample size is huge, very trivial differences are going to be detected. And you're going to get this red flag saying,
"Oh no, you violated normality assumption." Ah!
Even if it's a trivial difference. So that sucks. And problem number 3. This is probably the biggest problem. And this, to me, is what renders tests of assumptions completely and utterly useless. The third problem with these tests is that they tell you what is detectable, not what matters, or what is matterable. Matterable. Consequential, that's probably a better word to use, but I like matterable because it goes along with detectable. So just because it's detectable doesn't mean it's matterable. That's a good quote. You should put that on a bumper sticker. Detectable isn't the same as matterable. When we are testing for assumptions... Okay, I'm going to go on a quick rant. I didn't plan for this, so we'll see where this goes. I have another problem with hypothesis tests. Maybe this should be number 4. I don't know. I have a lot of people who ask me questions on YouTube or via email or in person or whatever. And they really want to show that they did their homework. And a lot of times they say, "All right, dude," because some people call me dude. They say, "All right, I wanted to see if normality was a problem, so I did a test, and I violated the assumption of normality." And I can tell that some of these are very eager to show me how awesome they are, and how conscientious they are by doing hypothesis tests, and they want to give themselves a pat on the back. And I feel bad about shattering their illusions about how good they're doing. So that's the sort of thing. It gives people the luxury. It makes people feel like they're being really responsible, when really they're just evaluating whether the sample size is big. That's really what it's doing. And so good, conscientious researchers will often do this, not realizing that it's completely useless. Anyway, I guess that's all I gotta say about that. All right, p-values. These p-values that we compute are asking whether we can detect any violation of the assumptions. But just because we can detect it does not mean that it matters. Just because we can detect it doesn't mean it's going to screw anything up if we continued with the model anyway. Just because it detects it doesn't mean that we're making bad conclusions from our data. In other words, when we do a hypothesis test, it's really answering the wrong question. We don't care about the answer to that question. We don't care whether it can be detected. We want to know if it's going to screw things up. So what is the right question, sir? I'm glad you asked, especially in an English accent. I will always answer questions in an English accent. Well, I will answer questions asked to me in an English accent. I may not respond in an English accent, but maybe I shall this time. Well, what is the right question? That is a fine question to ask. The right question is, will these departures affect our conclusions? That's really what we want to know. We want to know, all right, is this violation problematic and will it affect my conclusions? If that is your question, which it probably should be, then hypothesis tests are meaningless.
Okay, I think I'm following, so... is there some sort of statistical test that we could ask to say whether it matters?
No, there is not a test. Nor should there be, because I don't like tests. I have a personal bias against tests. No, instead we're going to do a 2-step method. This is the Dustin patented 2-step method. Copyright, registered trademark, etc. Not registered at all. But it consists of 2 steps. The first step is to visualize the residuals. And if you don't know how to visualize residuals, then check out my diagnostics video, which will show you how to do that. And what we're trying to tell is if there are super large departures from normality or super large departures from homoscedasticity. Linearity is a different one. That's a little more sensitive. You should probably be a little more sensitive to linearity violations, but for the other two, the normality and homoscedasticity, if they're not massive departures, don't worry about it.
Okay, is there some sort of statistical test to tell me whether it's a large difference?
No, there is not.
Okay, so how do I know if it's a large difference?
It's going to take practice, my boy. Yeah, after a while, you're going to start to notice, like, wow, that one really departs from normality. We need to take care of that. Versus, that's a little minor deviation. We don't care. But fortunately, if you're unsure, you can move to step 2 anyway. In fact, if you're a beginner, probably move to step 2 regardless. And then with practice, and after you've done this several times, you might say, you know what? I trust my gut on this one. So step number 2 is to fix it and then compare the conclusions. So for example, if you're trying to address normality, you might do a transformation and then fit a model with a transformation and compare it to a model without a transformation. And if the two models are basically making the same conclusions, then it doesn't matter. And we call that a sensitivity analysis. Sensitivity analysis just means that you fit the model addressing the issue and then you fit the model not addressing the issue, compare the two and see if it really matters. And so if you reach a point where the conclusions are the same, then don't worry about it. Just get rid of that more complex model, go with the simpler model, and decide, hey, that deviation from normality, I don't care. So, you probably want to see an example analysis, eh?
Well, I think that would be helpful.
It would indeed. So let's go ahead and step into R. Cool. Hey, we made it into R. That was fun. So I'm going to read in my data set. This is the health and depression data set. It comes from a paper that I will link in the description if I remember. If not, then you're welcome to bark at me. And then, as I always do, I'm going to start with the univariate plots and see what's going on here. I need to require flex plot. And then if I visualize that, oh boy, we got a problem here, right? We see that CESD, which is depression, is positively skewed. But it's actually not a problem. Because remember, we make the assumption about the residuals, not about the plots, or not about the raw scores. But that tells us that that could be a problem. We might have residuals that aren't normally distributed. Let's go ahead and look at IAT total scores. That's internet addiction. And same thing, we got a positive skewness, which actually isn't all that surprising that most people do not have depression, or most people do not have internet addiction, and then the higher you get, the fewer and fewer people have that. It's kind of common with psychological abnormalities, I guess you would say. And then we shall look at HPLP, which is health, and that looks a little more symmetrical, still a little positively skewed, but anyway, we're not worrying about that. And then let's go ahead and plot all the variables together. So we've got CESD on the x-axis, internet addiction on the, CESD or depression on the y-axis, internet addiction on the x-axis, and then we've paneled on health, and we see that there is a consistent relationship between internet addiction and depression. The more addicted you are to the internet, the more depressed you are, and I guess we could go method equals LM, because those look relatively straight. There's a little bit of bumpiness, but I'm not worried about that. And then we could go ghost.line equals red, and then just see how they change. So those aren't strictly parallel, so it might be worth evaluating an interaction effect. Actually, I'll go ahead and do that real quick. That's not the purpose of this video. I'm going to do it anyway. I'm going to create a model, and then a model with an interaction, and then a model without an interaction. So I'll call that mod and mod2, and then model.comparison, mod and mod2. And I'm just going to test that now. Now, you might be saying, whoa, dude, you're the visualization guy. What's the deal, dude? You're going straight to a test without visualizing it? Well, I actually did visualize this right here. And I can see that those are deviating very slightly from parallel. And I don't know, just by looking at that, whether that small deviation from parallel is enough. And so I've already visualized it. Now I want to test to actually give me a more concrete answer. So R squared, I'm only explaining 0.3% of the variance. P-value says don't keep the interaction. Bayes factor favors the smaller model, so that would also say don't keep the interaction. BIC says the same. AIC also favors... Okay, so all of them favor the model without an interaction, so we don't need to worry about that. Which means that tangent was unnecessary, but maybe it was helpful. Anyway, so yeah, we're gonna fit a main effects model, and then what we will do is study the residuals. Now remember earlier we saw CESD was positively skewed. Let's look at the residuals now. I'm gonna make that a little bit bigger. And of course my head's gonna be in the way. Let me move that. There we go, I've moved my head. Those residuals look a little more symmetrical, still a little bit positively skewed, especially if you ignore that outlier, but not that bad. And so I would, if I were doing this analysis, I wouldn't even bother doing any sort of, I wouldn't even bother trying to fix that. But you might not be in that position where you're ready to say, okay, I'm fine. In fact, we'll go ahead and do an Anderson-Darling test, and then I'm going to use the Anderson-Darling test. I don't recommend you do this. Again, it's completely unnecessary, but I'm going to show you what would happen. And we would say, oh dear, oh no, I violated the normality assumption. Look at that p-value, it's statistically significant. Because again, the p-value is evaluating the null hypothesis. Null hypothesis says that our residuals are normally distributed, and this p-value tells us it's able to detect a departure from normality. Again, I'm only doing this not because you should do it, but because I'm going to show you that it doesn't actually matter. Let's go ahead and use a model that fixes the problem, and then compare it to the model where we just ignore the problem. And so to do that, I'm going to use the mass package in R, and specifically the RLM, which stands for Robust Linear Model. I've made a video about robustness. I haven't exactly explained in detail what RLM is doing, but I'll link that video in the description so you can get an idea of kind of sort of what it's doing. And so I'm going to fit a model that basically does not make the normality assumption. Now that I fit the model, I want to visually compare the two models and see if they're really making any sort of differences. And so to do that, I'm going to use the compare.fits function. And so I'm going to plot it exactly how I did before with CESD on the y-axis, internet addiction on the x-axis, and then HPLP or health in panels. And then I'm going to now ask it to display the predictions for both the models. And if I do that, and then I'll go ahead and zoom in on this, and my head's going to get in the way again. So let me move my head to an ideal location. Right there. How's that sound? Okay, so we've got two lines. We've got a red line and then a bluish greenish line. And you'll notice that there's a whole lot of overlap, or they're nearly identical. So what is that telling us? That's telling us that when we fit the two models, both of them are basically given almost identical predictions. Okay, so according to that, it doesn't matter. But let's go ahead and kind of look at the summaries and see what the estimate. Actually, I guess the estimates might not be affected, because what could happen is that your actual regression lines don't change, but maybe like your standard errors will. So maybe your p-values and that sort of thing will differ. But of course, as you know, I'm more into model comparison. So let's go ahead and, I don't know if you can actually do a model comparison with an RLM. I'm going to find out. So I will do reduced equals, and let's say we want to test whether the inclusion of internet addiction is important. So I can do a model.comparison of the mod and then reduced. And so that tells us that we definitely should keep internet addiction. Let's go ahead and see reduced underscore fixed equals RLM CESD tilde, and then I guess I can just copy and paste that, and then data equals D, and then now to find out if this is actually going to work, model.comparison, and then mod fixed, and then reduced fixed. Hey, that does work. I didn't know that. I made up flexplot and I couldn't remember. Okay, it's not going to give you p-values in R-squared, but that's okay. If we fix the problem, we conclude that we go with a full model. If we do not fix the problem, we conclude that we go with a full model. So our conclusions are the same. We make the same substantive conclusions. The predictions are nearly identical. I guess we could look at the effect sizes. So we could go like estimates of mod, and I'll make that a little bit bigger so we can see it. And I guess my head is not in the ideal location again. I keep having to move my head. All right. So if we look at the estimates, this is for the original. We're explaining 17% of the variance. If I remember right, you don't get R-squareds from robust models. But we could look at, since I said earlier, internet addiction is really the thing. So you could look at the standardized estimate. So for every standard deviation increase in internet addiction, we expect a 0.4 standard deviation increase in depression. And if we did that for estimates of mod underscore fixed, what would we get? Oh, it's 0.41. So yeah, they're nearly identical. All right, so when we visualized it, the two models were nearly identical. When we did model comparisons, we concluded in both models the exact same thing. And when we looked at the estimates were nearly identical. So between these three things, I'm very confident that we didn't need to worry about normality at all, regardless of what the Anderson-Darling test said. So again, I rarely make... I try to avoid making very broad statements that are easily refuted, but I think this would be one where I'm confident that testing assumptions is completely useless. I don't think there's ever a situation where it makes sense to use one. Instead, I would recommend doing what I did, that if you're worried about it and there's evidence that you might need to worry, then fit a model both ways and see if it actually does make a difference. If it doesn't make a difference, just go with a simpler model. And you will probably be surprised at how robust linear models are, that even with massive departures from normality, it really doesn't matter most of the time. So anyway, yeah, that's all I got. Hopefully that was like awesome and helpful and stuff to you. Anyway, let me know if you have any questions or comments. Leave them in the comments below. And yeah. And of course, don't forget, if you want step-by-step guidance from me via a class you can take online through Zoom, please visit simplistics.net, where we have live classes where you do get to interact with me, or you can do a self-guided class where you get access to all my videos, all my quizzes, all my discussion boards, and that sort of thing, and you get to interact with me through typing. Typingly. You get to interact with me typingly. You get to interact with me that way. So anyway, hope to see you at simplistics.net. Until next time, peace out.